we've seen the general comparison test, and one of the issues with the general comparison test is that sometimes the terms in the sequence don't necessarily follow the descending the comparison to where a sub n is less than b sub n or b sub n is less than a sub n. But we still know that the behavior of the series b sub n is either convergent or divergent. So if that happens, then the general comparison test is inconclusive, but we can use this limit comparison test. We're still going to find a series to compare to, but we're just going to take the ratio of the original series or the original sequence compared to the compared sequence. If that limit as n approaches infinity is a real number, where c is greater than 0, then we can say that both of the series converge or both of the series diverge. All right, so when we're doing these problems, the first thing you probably want to do is find a compared series. Okay, so find your b sub n. Okay, now once you do that, you find the behavior of the series b sub n. Okay, and then you take the limit as n approaches infinity of a sub n over b sub n. Okay, so those are your 3 steps when you're doing the limit comparison test. Okay, it's a little bit more algebra and calculus than the comparison test, but it does work more frequently. Okay, the difference is that, again, if you have a rigorous series to work with, then the general comparison test might be easier. So examples. Let's take this series n equals 0 to infinity 2 divided by 4 to the n plus 2, and let's determine whether it's going to converge or diverge. First thing we're going to do, we're going to compare it. All right. In the numerator, we just have constants, so we're not worried about anything. So that's going to be a 1. Right. In the denominator, 4 to the n gets bigger much more rapidly than 2 does. So we're just going to worry about the 4 to the n. Okay, so that's the compared series. And the sequences that we're using are 1 over 4 to the n, and then 2 over 4 to the n plus 2. All right, so next thing we're going to do is we're going to determine, well, what's the behavior of the compared series? Okay, so this is I. Okay, so I. Okay, well, if we look at this series, another way to write this series is n equals 0 to infinity of 1/4 to the nth power. All right, and we know that this is a geometric series. Okay, so it's geometric. Right? We have r equals 1/4, and so it is convergent. Okay, so that's the behavior of the compared series, is convergent. So we're suspecting that the original series is convergent if, when we take the limit of the ratios, that's going to be equal to some constant c. Okay, so here's the hardest part, doing the infinite limit. Okay, so remember, this is b sub n, and this is a sub n, and we're just going to substitute those back into this rule. Okay, so we are going to take the limit. It's going to be a little bit ugly at first, but it'll clean up nicely. N approaches infinity. A sub n is going to be 2 over 4 to the n plus 2. So remember, that's a sub n. And then we're going to divide that by 1 over 4 to the n. Now, if we clean this statement up, we just multiply by the reciprocal, and this is going to be the limit as n approaches infinity of 4 to the n divided by 4 to the n, or 2 times 4 to the n, excuse me, divided by 4 to the n plus 2. To be able to evaluate this limit, we can divide everything by 4 to the nth power. Okay, so this is going to be limit as n approaches infinity of 2 times 4 to the n divided by 4 to the n divided by 4 to the n over 4 to the n plus 2 over 4 to the n. And so finally, we simplify, right? And we end up with the limit as n approaches infinity of 2 in the numerator, 1 as this term, and then 2 over 4 to the n. Now we apply the limit to this little guy right here. That goes to 0, and ultimately this is 2, okay? And 2 is indeed a real number, and 2 is greater than 0, okay? And remember, those are the conditions when we go back here. C is a real number, C is greater than 0, okay? So what that means is that because the compared series is convergent, and we have this real number that the limit of the ratios is equal to, and it's greater than 0, then the original series must converge as well. Okay, so in conclusion, okay, since the limit as n approaches infinity of a sub n divided by b sub n is equal to 2, which is a real number, okay, 2 greater than 0, and since b sub n converges, okay, then the series, remember the original series was n equals 0 to infinity, 2 over 4 to the n plus 2 converges, okay, by our limit comparison test. Okay, all right, so not too difficult. Okay, so hopefully that makes sense to everybody. Again, 3 steps: find a compared series, determine the behavior of the compared series, and then do the nasty sort of algebra / calculus to be able to evaluate the limit. Okay, and then we can extrapolate that the behavior is going to be congruent to the behavior of the compared series. All right, so we'll take a look at a couple more examples in the next videos, and then we'll be done with this section.